In our relentless search for clean energy, we often look to the simplest and most abundant element in the universe, hydrogen. On the surface, it appears to be the perfect fuel. When hydrogen combines with oxygen, it produces only water and a tremendous amount of energy. This clean, simple reaction has led many to champion hydrogen as the ultimate solution to our planet's energy needs. It holds the promise of powering our homes, our cities, and our vehicles without releasing the harmful carbon emissions that warm our world. The vision is a compelling one, a future powered by the very same element that fuels the stars above us. However, the story of hydrogen is far more complex than it first appears. Unlike the fossil fuels we have relied upon for centuries, hydrogen is not something we can simply dig out of the ground. It does not exist freely on Earth in its pure gaseous form. Instead, it is almost always bonded to other elements, most commonly with oxygen to form water, or with carbon to form hydrocarbons like natural gas. To use hydrogen as a fuel, we must first expend a considerable amount of energy to break these strong chemical bonds and isolate it. This fundamental truth is the first great challenge in the hydrogen story. The allure of a hydrogen-powered world is powerful. Imagine a world where the only exhaust from our cars is pure water, where power stations hum quietly, emitting nothing but harmless vapor. This vision has captivated scientists, engineers, and policymakers for decades. It suggests a seamless transition away from our polluting past towards a truly sustainable future. This dream is not without merit, for hydrogen is indeed a remarkable energy carrier. It can store energy for long periods and release it when needed, a quality that is immensely valuable in a world increasingly reliant on intermittent renewables like solar and wind power. Yet, we must approach this enticing prospect with a measure of caution and scientific rigor. Nature rarely provides such simple solutions without presenting significant hurdles. The journey of hydrogen from a bonded element to a usable fuel is a long and energy-intensive one. It is a process filled with inherent inefficiencies that we cannot ignore. Before we declare hydrogen the savior of our energy future, we must look closely at the true cost of producing it and converting it back into the electricity that powers our modern lives. The illusion of a perfect fuel begins to fade when we examine the intricate and demanding process required to harness its power. To obtain pure hydrogen, we must engage in a process of separation, which itself demands a great deal of energy. The most common method today is called steam methane reforming. This industrial process takes natural gas, which is primarily methane, and reacts it with high-temperature steam. While this method successfully produces large quantities of hydrogen, it comes with a significant environmental cost. A major byproduct of this reaction is carbon dioxide, the very greenhouse gas we are striving to eliminate. This form of hydrogen, often called gray hydrogen, contributes to the climate problem rather than solving it, unless the carbon is captured and stored, a costly and complex addition. A cleaner, more hopeful path to producing hydrogen is through electrolysis. This process uses electricity to split water molecules into their constituent parts, hydrogen and oxygen. If the electricity used for this process comes from renewable sources like solar panels or wind turbines, the resulting green hydrogen is indeed a very clean fuel. However, we must confront a fundamental law of physics. The energy required to split the water is always greater than the energy we can get back from the hydrogen produced. This is a crucial point. We are not creating energy. We are simply using one form of energy to create an energy carrier, losing some in the process. This energy penalty is not insignificant. Electrolysis, even with the most advanced technology available today, is only about 70 to 80% efficient. This means that for every 100 units of electricity we put into an electrolyzer, we only get 70 to 80 units of energy stored in the resulting hydrogen. We have already lost a fifth or more of our precious renewable energy before the hydrogen has even been stored or transported. This initial loss is a substantial obstacle, making green hydrogen an expensive proposition from the very start. The dream of clean fuel is tempered by the reality of this energy conversion tax imposed by nature. Therefore, the creation of hydrogen is not a source of energy, but a transformation of it. Whether we use fossil fuels and create emissions, or use clean electricity and accept an immediate energy loss, there is a cost. This is fundamentally different from harnessing wind or sunlight directly. Solar panels and wind turbines capture primary energy that is already present in the environment. Using that electricity to then create hydrogen adds an extra, inefficient step to the process. It is like taking a bucket of water from a river, using it to turn a small water wheel, and then claiming the wheel is a new source of water. Once we have gone to the great effort and expense of producing hydrogen, another challenge awaits: turning it back into useful electricity. This is typically done using a fuel cell, a remarkable device that reverses the electrolysis process. Inside a fuel cell, hydrogen gas reacts with oxygen from the air to produce electricity, heat, and water. It is a clean and quiet operation, but just like electrolysis, it is not perfectly efficient. Even the most sophisticated fuel cells today lose a significant portion of the hydrogen's energy as waste heat. This is the second major efficiency loss in the hydrogen for electricity cycle. Let us consider the entire journey, from start to finish. We begin with clean electricity, perhaps from a solar farm basking in the sun. We lose around 25% of this energy when we convert it into hydrogen through electrolysis. Then, we must compress, cool, or store the hydrogen, which requires yet more energy. Finally, when we need electricity again, we run the hydrogen through a fuel cell, where we might lose another 40% of its stored energy as heat. When we add up these losses, the round-trip efficiency, from electricity to hydrogen and back to electricity, can be startlingly low. In the best-case scenarios, we might only get back about 30 to 40 units of electricity for every 100 units we started with. More than half of the original valuable renewable energy is lost along the way. Compare this to a modern battery. When we charge a battery with 100 units of electricity, we can typically get back 80 to 90 of those units. The process is far more direct and vastly more efficient. This stark difference in efficiency has profound economic consequences. Wasting more than half of your energy means the electricity produced from hydrogen will inevitably be much more expensive than the electricity used to create it. This inherent inefficiency makes it difficult to justify using hydrogen for large-scale power generation in most circumstances. Why would we take clean electricity from a wind turbine, go through a lossy, multi-step process to turn it into hydrogen and back, when we could simply send that electricity directly to the grid or store it in a much more efficient battery? It is an incredibly roundabout way of moving energy from one moment in time to another. For the simple purpose of powering our national grid, the hydrogen cycle as it stands today represents a significant and costly waste of our precious renewable resources. Despite these significant limitations, it would be a mistake to dismiss hydrogen entirely. It possesses unique properties that make it the right solution for specific, challenging problems where other technologies fall short. Its primary advantage is its ability to store vast amounts of energy for very long periods. While batteries are excellent for storing energy for hours or even days, they become prohibitively large and expensive for storing energy across weeks or months. Hydrogen stored in tanks or underground caverns can bridge these long seasonal gaps, saving surplus solar energy from the summer to warm our homes in the winter. Furthermore, hydrogen is an energy-dense fuel by weight, making it a promising candidate for decarbonizing sectors where batteries are simply too heavy. Long-haul aviation, international shipping, and heavy-duty road transport are all areas where the weight and limited range of batteries present a formidable barrier. For a large container ship crossing the ocean, or a lorry traversing a continent, tanks of liquid hydrogen or ammonia, a hydrogen derivative, could provide the necessary power and range without the immense weight of a comparable battery system. Here, the lower efficiency is a worthwhile trade-off for enabling zero-emission transport. Hydrogen also has a vital role to play in heavy industry. Processes like steel manufacturing and fertilizer production currently rely heavily on fossil fuels, not just for heat, but as a chemical reactant. Green hydrogen can serve as a direct replacement, providing the intense heat required for furnaces and acting as a clean chemical feedstock. In these applications, it is not being used for simple grid electricity, but as an indispensable industrial tool for decarbonization. This is where hydrogen's unique chemistry, rather than its potential for power generation, truly shines. It allows us to clean up industries that electricity alone cannot easily fix. So, we see that hydrogen is not a universal cure for our energy woes, but rather a specialized tool for specific tasks. For the broad purpose of generating electricity for our homes and businesses, direct use of renewables and battery storage is far more efficient and economical. The idea of a widespread hydrogen economy, where it serves as the primary energy carrier, overlooks the fundamental energy losses involved. Instead, The future of hydrogen lies in these crucial niches: long-term energy storage, heavy transport, and industrial processes. By applying it wisely where it makes the most sense, hydrogen can and will be a vital player in our journey towards a sustainable planet.